There are some procurements out on the street so that we don't want to talk about. So if everybody could be mindful of that we don't want to cross the streams here. And so just let's kind of not talk about anything that's blacked out.
Yeah. All right. Let me know if I cross the line, but nothing's coming to mind that I would mention. So, hey, thanks, Bruce, for that kind introduction. And I'm actually going to start by talking a little bit about my background, since it is a little unusual compared to a lot of the people whom I've met in the space industry and who are on this call. But I'm excited to be part of it. It's been sort of an interesting few-year journey for me. And I am continuing to work sort of in terrestrial spheres as well, but expanding my practice in space. And actually I have a few funded projects now working on different aspects of space technology and space settlement. So I'm excited to share some of that context with you, and specifically a modeling tool that I've been developing probably for the last 3 years that's now an actual tool as opposed to just more of a concept. So, all right, let's see. Let me advance the slides. Okay, so my background and journey into space. So I'm American. I was born and raised in eastern Pennsylvania, outside of Philadelphia. Spent all my childhood years kind of near forests and fields and things like that. Spent a lot of time outside. I think developed a love of nature and the environment that way. I went to a bucolic college near my hometown where I majored in physics and chemistry. Obviously, early interest in the sciences that has continued to this day. When it came time to decide on grad school, I rather almost by accident chose Berkeley. I had gotten into a number of schools both on the East and West Coast, and I was really just fascinated by how different it is out here in California, and for various reasons just decided to relocate and kind of be a pioneer and explore a new area of the country. And I don't regret my decision for one moment. Got a PhD in chemistry, which has kind of come back to serve me well in this more current context. But at the time, I initially applied it to understanding ozone chemistry. And my first postdoc after grad school was actually at NASA Ames. And it was an atmospheric measurement campaign, flying the ER-2 high altitude research aircraft around the Arctic stratosphere. We were based in northern Sweden, and I spent a lovely winter there looking at the northern lights and ice hotels and dog sledding and things like that in between all the research that we were doing. But then I became interested in climate change as a real difficult unsolved problem, and quite a bit, in my view, more important than ozone loss, as important as that is, because it affected so many of us in such fundamental ways. And so I was fortunate enough to have a second postdoc opportunity at Princeton University, where I studied climate change head on, and then that kind of morphed into understanding carbon reduction strategies, which is sort of paved the way for much of the rest of my career. So after my training, I spent some time at Environmental Defense Fund looking at greenhouse gas mitigation strategies. Did similar kinds of things at Google, where now the emphasis was on investing in renewable energy research and companies. But then kind of switched into research, where I spent more than 8 years at Berkeley Lab and really expanded my skill set into things like energy economics, life cycle analysis, and study of emerging technologies. And I would say that latter piece was really kind of the key that got me thinking more about space, because I kind of had a nose for things that had not yet been appreciated in the public as a technology that was recognized as having a big impact. It was kind of like on the side. Sometimes it was even in the research stage. An example of this is autonomous vehicles, which I started researching in 2013, 2014, and then wrote a paper about that kind of showed what the reduction potential for this would be. At the same time, I was thinking about a lot of other emerging technologies. And you're absolutely right, Bruce. It was Elon Musk, I think, who probably was the first person where I was reading about what was going on at SpaceX and just became completely fascinated thought, wow, if this is not like a potential huge change to not only space, but potentially our economic framework, I don't know what is. And so I went to my first New Space conference in 2015, where I heard from a lot of other companies, both large and small, doing interesting things in commercial space, and got completely hooked. And since then, it's really just been a wild ride where I've been wanting to find a way to make a professional contribution, and I think I've been able to do that. So I founded my own company in 2016 and then went full-time earlier this year, and that is a consulting company I'm calling Emerging Futures, looking at the various futures, both in Earth and space, that we might have a chance to bring into reality. So, with that as background, let me tell you a little bit about the modeling tool I've been developing as one of the tools or products that Emerging Space is excited to share with you. So I believe that there's a need for a new set of space simulation tools or models. You know, I kind of started building this just cobbled together from the bits of information that I had in order to understand some things like how much, you know, propellant does it take to send people to Mars, and what's the spacecraft infrastructure required on the other end. And it's really hard to answer these questions without a model, particularly model where each piece is kind of well vetted. And so, you know, the models that I've been able to identify that sort of focus on this in some way, focus, as I understand it, on space transportation, so logistics, but kind of heavily on emerging technologies. It's not, existing technologies. It's not entirely true, but the ones that I've identified, early one that crossed my desk was something developed more than a decade ago at Marshall Space Flight Center called ATLAS, which is a life cycle analysis system that allows you to build campaigns. And it's a very useful tool, but it's kind of focused on things that NASA does now. It's not really geared toward the large scale human-oriented space exploration and economic activities that I'm interested in anyway, and I think others are as well. SpaceNet is an interesting tool developed by MIT most recently. I don't know how much it's supported today. It does have a very good logistics engine, much better than what I've been able to build, but again, it doesn't really focus on the pieces of technology that are needed to sort of make economic transformations happen. And so it's limited in that way. And more recently, I had come across some work by Koki Ho at Champaign-Urbana, who's also doing kind of like a logistics optimization model. And this is interesting because it's really trying to find sort of an optimal global, you know, solution to, if you have so much stuff that you have to move from certain locations to certain other locations in time, it can help to work that out. But again, it's focused on sort of the movement of goods in space, which is obviously a very important one. I'm more interested in the kinds of equipment that you need in one location in order to accomplish transformations that are important for human life support, or for ISRU or other activities kind of related to a long-term presence in a location. Not that it excludes transport of things from other places. That's obviously a key to any sort of space economy as well. But so, I mean, kind of with this as background, I decided, you know, I'm just going to put together what I need and see where this goes. And so what's emerged is a model, which I'll describe on the next slide, that addresses the large-scale space operations with really an emphasis on human habitation, although it's not just that, not limited to that. And it emphasizes kind of front and center ISRU of different kinds, and I'll talk about what some of those are that I've modeled. Takes full advantage of opportunities for material reuse and recycling. So one system's waste is an input for another system whenever possible. It uses both. I'm just pausing because we got some feedback there. Is that gone now?
You're good.
Okay, I unplugged and replugged my microphone. The model also has a mixture of both current and future technologies embodied in it. Future, of course, not being such as depicted there in the graphic, but things that may be emerging in the next few years that are not yet operational, that may be a company technology and development, or something that's kind of at the upper end of the research stage that looks like it could be commercialized. The physics looks good, the economics, maybe there's a fair chance of that. And so to some extent, I've represented some of those as well, and we can talk more about that. Another thing that's really important for this model is that we are not just looking at things happening at pilot scale or sort of on the order of supporting one or two people. It's really kind of system operations at large scale. And so I am borrowing from Earth Analogs a lot of information. What would a full-size factory look like on the surface of another planet in order to do tons per day level production of materials processing, for instance. And finally, and this is something that's still being developed, but is an aspirational goal of the model, is to do cost projections, particularly as scale increases and costs can come down, learning rates and so on. It'll be very important for us to understand what the projected future costs of these operations are. And so that's something that I've kind of built into the framework from the beginning. Doesn't have very much cost information in it yet, but we're going to get there. Okay, and so these are the elements of what I think a modeling framework is needed. Now let me tell you what my model is and what it does right now. So I'm calling it ASTER, which is kind of a fabricated acronym, but it captures the essence of it: analysis of space technologies, economics, and resources. As I said, it is a framework that simulates all these things associated with constructing and maintaining complex space systems. And it can be in greater or lesser detail. We could build the model to simulate a lot of the subsystems of the ISS, for instance, as shown here, but really we're more interested in things at a sort of more aggregated level, such as a human research base on the moon, or asteroid processing capabilities, things like that, or even the trade of different activities among locations in space. So the idea is complex space systems with a lot of subcomponents that can be modeled and resources tracked. It draws from a growing database of technology components. We're adding to this, every few days. Another technology that I read about, or my team, has developed a way to describe in the framework of the model, and we put that in, and now it's another technology that we can pull off the shelf and link together to the other pieces. And it's useful for various ways. It's also a way to kind of track the progress of these technologies as they might move from the research stage to commercial development and deployment. So sort of TRL tracking, and a number of launches, things like that. One of the things that ASTER will allow us to do is to use local properties in order to customize how a technology operates. A good example of that is differing levels of sunlight on different locations, but also the regolith composition, surface gravity, surface pressure, temperatures, things like that are really important to sort of set the expectations of how well a technology will work, what components will or won't be easy to generate, et cetera. And so sort of have that fully integrated with a set of local resource assumptions. Because we have this library, many of the technologies being kind of duplicative or overlapping in their capabilities, we have the ability to do trade studies. And so, it's relatively easy for us to ask, gee, we don't know the best way to make, say, steel from indigenous resources. So we're going to compare 2 or 3 different pathways, maybe the same pathway, but with a couple of different technologies on offer. And so that's obviously important to just about any study. You don't just want a single set of assumptions, and ASTER allows us to do that fairly easily. As I think you're getting the idea of, it's built to be quite modular, and can also be scaled to essentially any size. All the components are basically linear, so you can have one of something or a million of the same thing. We also have the ability to sort of substitute out larger versions that might be more favorable in terms of their scaling. Like you can have a small scale plant, which then gets replaced by a larger scale plant that has better efficiency, for instance. But the whole thing is done in a way that allows you to plug and play. And all of the modules or as well documented as is possible, so that the system should be fully transparent and defensible if people want to sort of find out where all the numbers came from. And we can add to it at any time. And finally, again, more aspirational, it does have the ability built into it for adding space logistics and time evolution of system components, as well as a full-scale optimization. And so these are things that we want to add to the system eventually. So, all right, so just a little bit more about this before I get into the specific example of simulating a Mars colony, Mars settlement. Just kind of a different view of sort of how it works. It's built sort of from very, very basic components up to large system components. So there's a little notional, but the idea is that you start with elements, you build compounds, pure substances from that, and then those get combined into sort of the raw resources, which are mixtures of these substances. Those are sort of the basic building blocks, which technological processes then act on in order to make things that are actually useful, things like steel, polyethylene, et cetera, which ultimately turn into products that have the capabilities that we need. And at all the stages of this of production, we have output of materials, some of which can be reused and recycled into other processes. And so that's why I have the loop going back here. In addition to material, we also have energy, which is super important. And so we kind of have a similar chain for this. Energy is much more simplistically represented at the time. It's really just kind of like electricity, heat of different temperatures. Maybe we'll have laser beams of different wavelengths available there, radio signals, et cetera, especially for dealing with things like power beaming, where that can become important. But it's not just limited to substances. And then there's kind of like intangible elements as well, processes that take finite amounts of time. There's sort of a time component to it. Money is going to be something that we're trying to fold into all of these different processes. And then other things like labor, or even the requirements of data flow, bandwidth, et cetera, are going to be things that can be easily added and tracked in the model. And then we have things like the location, the state of matter, and some sort of other kind of tags like who owns this, where did it come from, specific tech specs if you have different versions that are all tracked as well. All right, and so kind of with that context, I'm happy to answer more questions at the end if people want to dig in a little bit. Here are some examples of scenarios that can be modeled. I've done some of this. Not all of these have already been done, but it's all within the capabilities with some further development. Transport of cargo and humans, say, to or from the moon or Mars. We can model asteroid mining and the associated transport operations. Spent a lot of time looking at how to produce refined materials from raw resources in situ on the moon and Mars, for instance. Construction and operations of a large space structure, such as a commercial space station or a propellant depot or a space settlement. Really kind of what ASTER was designed with that in mind. And similarly, things on the surface of the moon or Mars, including things like robotic mining operations, but human as well in most cases. And as we've been saying, cash flow analysis and investment requirements are going to be an important thing for it to be able to do eventually. Given, however, that it is often very difficult to do because of the very limited data on actual costs of each of these components. So that's mainly why it's a work in progress. But I'd love some input on how to be able to get that more systematically. Just a snapshot here, the current version of ASTER, it's got a lot of these pieces involved. I'm not going to walk through this, but just a glimpse, you can kind of see what pieces are represented and the general flow of information. All right, so maybe I should, I don't know if I should pause here or I can just jump in with, I'm about to talk about the Mars city now. So anybody have a question right now they want to interrupt?
So Jeff, could you talk a little bit about the color code there on that chart?
Oh, the color code. Well, it's the colors are less important. I mean, this is really just a way of sort of categorizing things like, water is blue and like fuels are orange. Things that are organic, I've kind of captured as green, but really this is just sort of to break up the monotony of the different labels. The really important thing is the kind of the 4 vertical categories. We've got sort of input assumptions on the left. We've got representations of different facilities or kind of equipment in this sort of gray color on the left side of inside the model. And then on the right side, in these more colorful components, are the actual flows of the resources that are produced or otherwise handled by these facilities on the left. And finally, some, but not all, of the key outputs from the model on the right-hand side. So does that help a little?
Yep, it does.
Okay.
One other question. One of the things we've been thinking about, Jeff, which it looks like you have in your model, is this idea of off-world concrete.
Mm-hmm.
Start thinking about any type of a planetary, maybe an asteroid type facility, handling landing pads, and I mean, just like we do here on Earth. I mean, concrete is a really important commodity when you're putting facilities in place.
It sure is.
So, this idea of being able to do concrete on the moon at, large scales, particularly if you're looking at things like these large rockets now, like SpaceX's.
Yeah, BFR. Yeah.
How, landing something like that on the moon without a landing pad could probably be problematic. And so I think that's really interesting to see that that's in your model as well.
Yeah, completely agree. I mean, I do have a chemistry background. I can follow a lot of the chemical transformations that people have explored in terms of how would you make concrete given, the lunar resources that are available or the Martian resources. I've kind of glossed over some of the hard details and just said, look, and a hard detail might be the fact that you're working in a vacuum environment. The way you would set concrete on Earth is you mix water with the, with the cement and aggregate and allow it to cure. That's going to be hard in a vacuum because all the water evaporates.
The water will go.
Yeah, not to mention some hard, some difficult temperature gradients. And so, one would have to think about how this would actually be done. Maybe it would have to be done under pressurized domes. Right. And you would set them. I mean, these are sort of practical engineering questions that I don't think are insurmountable. And so what I focused on is if you made concrete similar, but not exactly the same way that you do it on Earth, that is, you're limited by the actual chemistry of the regolith, just focus on the material and energy requirements of that process. Right. And there may be some things that are not that straightforward to do. Getting from A to B could be a difficult bridge, but yeah, I mean, I've acknowledged that having a way to make concrete or some other consolidated material, it could be sintered regolith. I mean, I'm not opposed to just doing something that's done that way instead, and it won't be as high performance as concrete, but it might give you the it may address the problem of having all the dust get kicked up. And so, right. I'm open to a lot of those different options, but I guess I'll say I'm less interested in the method of actual production of the finished product. Like, there's a lot of excitement about 3D printing right now, but what is often, I think, missing in those discussions from what I've seen is, well, how do you get the substrate in the first place? Like, that's usually a pretty high performance material. And it really doesn't matter how you finally lay it down, but if you can't make the input material well, then there's really no point, right? So whether you 3D print the thing or you lay it into molds or you put it in these pressurized domes, like I was saying, is less important than how you make the raw materials in the first place.
Jeff, this is Alex Ignatieff in Houston. In your facilities and in the scenarios you mentioned in the previous slide, I see one thing that is critical, but is kind of at the bottom of the list. And whenever I've given talks about space and how to utilize space, the 3 main things I've always identified as required is number 1, electrical energy, number 2, electrical energy, number 3, electrical energy.
Yes.
None of the facilities you have there, nothing can be done without energy input, and you've got to have it first.
It is the key input assumption going in that we will have electrical energy, of course.
From where?
That could be a whole discussion. I am currently planning to use a solar PV system to do it. but I do have a couple of different kinds of small modular nuclear reactors in the model as well. Yeah, and I think depending on where you are, and I think also it's a question of the longevity of the system and the servicing requirements, because they have trade-offs. I think that nuclear is wonderful for many reasons. You do have to have, of course, a supply chain to replenish the fuel. It may not be very much in terms of mass, but you probably are going to not be able to make your own nuclear plants for a very long time. It's a separate discussion. I have some assumptions in here that you would eventually be able to make solar PV grade silicon so that you could make your own solar power.
And that's a great input, because next week I'll be talking about how to make solar cells on the moon.
Oh, fantastic. All right. I will look forward to tuning in.
Jeff, there's one other thing that we've been looking at is, now it turns out that there are some nuclear materials on the moon, like for instance on the far side near the North Pole, there's a large thorium deposit. So one of the things we're looking at is, there's a lot of legal and regulatory issues around, launching materials into space. But what if you could launch just the reactor and actually get the nuclear material that you wanted sourced from the location?
Yes.
So there's some interesting kind of hybrid models there.
There sure are. Yeah, and as I understand, not an insignificant amount of uranium co-located with that thorium. So it's a big. I was aware of that. I drew the line at, boy, that sounds like a really big leap. In terms of processing, to be able to say that you can make enriched uranium from lunar regolith. So I think that that's something I would be very interested to explore, particularly if a company is trying to develop a concept company or NASA center. So love to hear if there's some thought leadership there. But yeah, and then the other question is, do we know of any comparable resources in asteroids or on Mars? I mean, so far, I think we've only really been able to identify this on the moon's surface, but perhaps there are radioactive resources elsewhere that we might be able to take advantage of. Do you know? Anyway.
Do not know that.
Our colleagues at NASA Glenn would probably have more information on that. So.
Okay. NASA where? Sorry?
NASA Glenn.
In Cleveland.
Yeah. Okay. All right. Maybe I'll follow up. That would be great.
Sure.
Jeffrey, this is David Chevron. I have a question for you on other kinds of materials that I don't see on the matrix here. And that is just all the huge number of chemicals and oils and paints, lubricants, paints, paper material. Have you given any consideration to how much of different kinds of things that are really needed to be able to have a viable settlement, and how we could get some of those kinds of materials?
Yes, I have actually. Thank you so much for bringing that question up. I've actually been delving into basic industrial chemicals very recently. It hasn't made it into this model yet, but kind of started out thinking about ways to make some useful plastics. Polyethylene is perhaps one of the easiest ones to make, because you can make ethylene along with methane fairly easily from an electrochemical cell that reduces CO2 in water. Some other kinds of chemical polymers, however, aren't that difficult to make as well if you have essentially a Fischer-Tropsch process that turns hydrogen and CO into straight chain hydrocarbons, and then do some cracking downstream of that to make things like benzene and other unsaturated small hydrocarbons, butadiene and so on. So I have been thinking about that, and I think that there is a pathway to making a lot of very useful industrial chemicals, both organic and inorganic. We've got a lot of alkali metals, as well as halogen, containing minerals on most of these most of these surfaces. And so things like getting chlorine and sulfur and so on are relatively straightforward just in terms of elemental abundance. But it's a huge topic, and honestly, I would love to work with an industrial chemist who is interested in this topic and kind of figure that out together. And get more familiar with the established literature on this for off-world. So if you have any suggestions, David, I'd love to hear.
Yeah, I mean, I have a book that's from my college days. It was a material engineering handbook, and I think it's probably 3 inches thick with all kinds of materials in it, all of which, really when you start looking through the book, seem like they're pretty essential for
Yes.
human civilization.
Yeah, I completely agree. I mean, this is really just a snapshot, extremely dumbed down to like, steel, concrete, glass, and a few other things, as you can see here, and it's a starting point. I tried to do it based on raw bulk mass that you wouldn't have to bring from Earth, but I agree. I have an earlier effort that tried to quantify some of the required flows of other materials, just based on yearly output from globally for things like sulfuric acid and some other bulk chemicals. But it's hard to put together a complete model without a little more knowledge. So if you want to talk afterwards, I'd love to have a conversation.
Jeff, this is Brad Blair. I'd like to suggest that you read or get a copy of Donald Rapp's book.
Okay.
On the topic of Mars ISRU. He goes pretty deep into a lot of detail into process chemistry. Furthermore, I would suggest that you look into the work of Pioneer Astronautics and Bob Zubrin's group.
Yes.
Who's really integrated in a lot of the microgravity and low gravity experience, as well as built a fair amount of hardware testing a lot of the processes for reforming hydrocarbons into useful materials, starting with CO2. Bob's been building prototypes under NASA contract since the early 90s when he was working with Lockheed Martin, and has a lot of hardware under development that's been put up to maybe TRL 5 to 6 level. I think understanding how his hardware works in terms of the models is pretty important.
Great, Brad, thank you. Yes, I'm aware of some of Pioneer's work and have been very impressed with it, but was not aware of the full scope. So yeah, I'm in touch with a few folks there besides Bob himself, and I'll follow up. Thank you for pointing me to that.
Jeff?
Yes?
This is Doug Plata.
Hey, Doug.
Yeah, hey. I wanted to just address back to the working environment. I could chat with you about how like a Zeus-sized lander could be able to retrieve the outermost layer of a large inflatable habitat, and then later layers could go inside, the Kevlar restraint layers and the airproof layers. And by my back of the envelope calculations, you could create an inflated environment with about 3.5 acres of footprint. So I could imagine that you could create a fairly sort of Earth-like environment in terms of the air pressure and as well as protection from radiation if you have telerobots covering the environment with regolith,
right,
or the roof with regolith. And so it may be possible to actually create a sort of an environment in which processes that we use on Earth that you can have people working within that environment.
In other words, with minimal modifications, because you've got an Earth-like environment to work in, so you don't have to design things to work at super low pressure, for instance.
Right, commercial off the shelf sort of stuff.
Yeah, great, Doug. I mean, one thing that I'll say, and then I think I want to move on. So hold your questions if you have more of them until a little closer to the end. Is that this model is extremely flexible, and so I'm not committed to one particular method. In fact, if a better one comes along, that we can get the representative data for, I am more than happy to replace the kind of proxy process that I have with something that is more credible. And so the nice thing about this is that I'm not advancing a particular framework or technology suite. It's really sort of just to be used to explore different combinations, or it's kind of to constantly improve the overall process to identify the best methods for the environment. So all these suggestions can be sort of employed relatively quickly. So thank you for all these. All right, so now I'm going to talk about some of the work that I've done in modeling the construction of a Martian city. And, you know, this kind of harkens back to how I got started in this field about 4 years ago, you know, hearing what SpaceX was up to and their audacious plan, not just to build the world's biggest rocket, but to build a city of 1 million people on Mars. And this question has just captivated me, as I'm sure it has many of you, ever since, asking the question, okay, let's forget about why or how we would do it financially or, you know, other things. What's needed to really make that a reality? And we haven't seen very much from SpaceX or others in terms of the actual equipment on the ground to maintain a population that large, let alone, you know, even a couple dozen people, but we're going all the way to city scale. And so the way I tend to work is sort of large and conceptual and then sort of honed down later. So I've started with sort of this huge reach goal of what would 1 million people look like? What are all the facilities needed there? And then you can kind of downscale to how it might be built up over time. And so that's the method that I'm going to present here in this remaining half hour or so. So we assume that it isn't just static at 1 million, but there is a net positive population growth that kind of takes us through this 1 million mark, albeit a little slowly. So I'm kind of assuming a growth rate of about 3% per year on net, given the differences between these different factors here, including immigration. That we, at this point, would be making maximal use of in situ resources for all of the things shown here: structural materials, you know, human life support. We'd be growing most of our own food and fiber, maybe producing some medicines, maybe still importing some that are difficult to make, particularly in small quantities. Propellant for surface operations, as well as spacecraft returning to Earth. There would be a constant reuse of these spacecraft as SpaceX envisions, and eventually making your own power, solar PV, so that you can grow your power needs indefinitely. And of course, to minimize how much you have to import and really just kind of keep it to people who want to move there. In all of this, I've just been assuming the use of the SpaceX BFR with the 150-ton capacity to Mars as a utilitarian, you know, human-rated spacecraft that can also transport large amounts of cargo. And we kind of understand how to model this because we know about the refueling capabilities, the fact it can land on Mars, it's designed for multiple uses, the round trip time within one synodic cycle, et cetera. And so I really like that framework. Of course, I can use other spacecraft paradigms as well, but this is the one I've modeled so far. And just very briefly, you know, I have modeled sort of aspects of this problem previously in a few other contexts, and just wanted to flash this up here in case people were curious where this came from. It's not the first time I've been looking at that. So the first question is, do we model one settlement or many? I think it's more realistic to assume that if you're going to have 1 million people on Mars, they're not all going to be sitting in one place. You'd probably have at least a couple of settlements, if not a large number, sort of distributed around the planet for both economic, cultural, and scientific reasons, with ability to transport between them. But that's kind of getting a level of detail beyond where I thought was necessary in this first cut. So it's just easier to model everything in one place, bearing in mind that if it was distributed, the total amount of resources, production capacity would basically be the same. The only difference is you would also have to have some transport intercity that's would add a little bit of additional resource demand there, but it's not a huge game changer in my view. So data sources. This is cobbled together from a variety of things. These are not all necessarily consistent, but it's where I was able to find data. Some of the information I have hired engineers to help sort of adapt information from Earth systems, particularly cement and steel plants that were adapted from industrial size plants on Earth, with some allowances for the difference in local conditions, as it were. Launch pads, we were asked earlier. I've kind of adapted parameters such as the amount of concrete that you need and associated infrastructure from data I found online about the Kennedy Space Center complex. Human habitats, sort of square footage, and other sort of associated structures, open space, roads, etc., mostly came from the 1975 summer study by Gerard O'Neill and coworkers. I thought was helpful to just sort of adapt here. It formed a starting point. And you can see where some of these other data sources come from. It woefully incomplete, but at least is a starting point for describing this. And this represents most of the elements that are in the model right now. So habitat assumptions. We could spend the rest of the talk and then into the next hour, I'm sure, debating what the right assumptions are. I'm just here to show you what I've assumed for the moment. Recognizing that radiation and micrometeorite protection is paramount. I have assumed a thick regolith layer on top of the habitats that basically create a large open space inside. So because resources are plentiful here and it doesn't take much energy to sort of compact and plow this on top, this is a steel structure skin, which on top of which is placed about 3 meters of regolith and periodically blocks of thick glass that perform the same amount of radiation shielding but allow some natural light to come through. This can be spec'd at various sizes, but some engineering colleagues of mine have designed a system that would work to support the weight and hold back the pressure, for a 50-meter diameter sort of footprint here, with an underground area of about 12 meters. You could do this entirely underground and have sort of some access channels to pipe light down. There are a lot of different approaches, but this is just one concept that we've modeled here. Inside, there will be plenty of room to create multiple layers, multiple levels of shops and living space, subway stations, et cetera. So you can think of this as a really vibrant city with a diversity of structures inside, all basically at earth pressure, shirt sleeve climate, with about 6 levels on average. So sort of 6 square meters of floor space per square meter of actual footprint on the ground. And the agricultural areas, as Bob Zubrin pointed out to me recently at a talk I gave last month, does not need this thick shielding necessarily. And so I've modified this to include a much thinner layer for the greenhouses that would actually encompass the majority of the footprint of the entire settlement. So the question is, how do we build all this surface infrastructure? And what I realized in early conversations with a couple of industrial experts is that industrial facilities on Earth are mostly made of concrete and steel. Even concrete and steel plants are mostly made of concrete and steel. And so this suggests that there is a bit of a bootstrapping approach that can be made. If you can make concrete and steel, even in small amounts, you can then make the beginnings of almost everything else that you're going to need. You can make larger versions of themselves. You can make other kinds of manufacturing facilities and kind of keep the specialized equipment to a minimum. And so then the question is, well, what's needed to make these materials? Obviously, we start with a source of power, and I break this into electricity and heat separately, although it could all be modeled as electricity, even though that's not necessarily the most efficient. These are then used to power the excavation and capture of regolith and atmosphere. The regolith is crushed, and from this, with some fairly simple heating and processing, you get calcium oxide and a mixture of other oxides, which in a cement plant, and basically heating it to the high enough temperature gives you cement. Then from the regolith, we're also making or extracting some water if we have water in the resource in the right locations, which is fairly plentiful on Mars. And water is an important component of making the finished concrete, plus some crushed rock. So that's how we make concrete in a very simplified manner. Now, to make steel, it's just a little more complicated. Steel is basically iron plus a little bit of carbon, and then you can have other alloying materials if you want, but sort of basic steel could be just these two. So you need a source of carbon. And on Mars, that's easy to get because you have lots of CO2. So provided that you can create a reduced form of carbon, in this case, methane, you need a source of heat anyway in a steel plant. So you burn this, you have some free carbon, you make your steel that way. On the moon, different story. Could be a lot harder to get sufficient amounts of carbon, but there are some resources for carbon kind of mixed in with the polar ice that might be sufficient. So that's how we make these two things. And then this is sort of the idea of building everything else. A majority of other materials can also be made indigenously, and I list these here. Haven't modeled them all, but the idea is that over time, most of these manufacturing capabilities do get built up until we're importing just a small amount of stuff from Earth that was just too difficult to get, or is made in too small of materials to really justify making it a plant locally. So your iPhones will probably continue to be shipped from Earth for the indefinite future until its population well over 1 million, probably 100 million. All right, so that's the idea. Now, it takes mass to save mass is kind of the next principle here. You know, if you want to be able to make a lot of, say, steel in this case, it actually takes quite a lot of mass in order to get to that point where you're making steel. So I'm starting at the large scale, and I'm actually going to go down to a smaller scale, but here's a commercial scale steel plant that we modeled based on Earth analogs that would operate in a Martian environment. And it's got a gross weight of about 1,500 tons. 75% of that or so is steel. The rest is basically concrete and a little bit of refractory material, and then motors and things. But in order to be able to support this, we also need a mining operation. We need a source of power, and that power both directly powers the plant, it also powers the mining operation, and it powers the propellant plant, which is necessary in this design in order to provide the carbon and a source of heat to the plant. And so now you're seeing that the amount of resource footprint is starting to really add up, particularly the solar PV plant, which is less than half steel. And then finally, heat rejection, because we have to get rid of that heat in an efficient way. So this is sort of like a bare minimum of things that we would need in order to support this activity. And we're not even saying there are any humans in the loop yet. That life support would then be in addition to that. But this would then give us the capability of producing almost 300 tons per day of steel, huge industrial level, much more than we need at the beginning. And at this level, we would be able to produce the amount of steel we need to build all of this facility in about 21 days of plant output. So you have a huge leverage once you're at this point in order to reduce the amount of mass that you would have to bring from Earth, because you can make it all here. But how do we get there from here? Well, the idea is basically to start small and bootstrap your way up. So now I'm showing the Pioneer Astronautics MAPS system that was developed a few years ago. I think they have better versions of this now, but this is what I was able to get. This produces a variety of minerals in addition, but sort of mainly iron through an aqueous processing system from Martian regolith. And this has a footprint of only about 1,300 kilograms as opposed to 1,500 tons. So we're talking a factor of 1,000 smaller. This can obviously be fit on a fairly modest payload to Mars. Now it does need other elements as well. It needs the mining, it needs electricity, a source of thermal heat, as well as a fairly modest amount of consumables, which are like parts that wear out, as well as acids and some things like that that you might not be able to make indigenously at first, and heat rejection. But you put all this together and you can make about 20 kilograms per day of steel. And at this rate, assuming that the other components, and I just sort of simply scaled it from the previous slide, you know, that the total amount of steel in terms of support you would need is roughly in the same ratio to the mass of the plant. You can make all the steel you need in about 240 days. And we're talking on the order of 5 or 6 tons of steel. So certainly something that could be brought on one BFR payload. And then you could make more of this on the order of less than a year. And so the concept here is that, you know, you're kind of slowly bootstrapping your economy. You bring these small size systems to the surface first, and you use that to build a larger version of itself, probably with a lot of telerobotics and maybe even human hands to sort of put it together. I'm not envisioning a total robotic economy here, because I think that's just a little too far in the future right now, although I'm open to hearing views to the contrary. And then you see that over time, eventually you're getting to the full commercial scale as your economy and your population grows. Similarly, you would have to do something with, say, a MAPS type cement plant that slowly grows until it's got an industrial scale plant, as well as systems to make these other components that you're going to need. And ultimately, you now have enough to build a settlement over time. So this is for the whole 1 million person settlement. And you can see that the numbers here are absolutely staggering. But the point is, you didn't have to bring it all from Earth. You only had to bring a small sort of seed corn, which builds the rest. So I used the model to simulate what the full 1 million person settlement might look like. In terms of footprint, this is kind of what it is a snapshot. We've got 100 square kilometer human settlement, which would be organized into 6 levels or so. So the total footprint on the ground is maybe 15 or 20 square kilometers. Agricultural areas, quite a bit larger. We've got an industrial park, which is fairly compact. We've got a spaceport for handling all the cargo coming and going. We've got a regolith mining operation. And somewhere in here, we have to reject the heat. It's sizable, so I kind of listed it separately, but maybe this would lay on top of parts of the human settlement and agricultural areas. Doesn't matter. And then the solar PV plant, which is absolutely huge. And this is not completely covered with solar panels. Only about a quarter of this area would be, but you need spacing in between for self-shading and access and so on. And compared to the city of Los Angeles, this is the size of the total footprint. Now, we have an empty planet, so there's plenty of room. But just to give you a scale of what this entire settlement might look like, it's on the order of 3,000 square kilometers. So I'll let that sink in for a moment. And again, because this has essentially been modeled linearly, if you're interested in what a 1,000-person settlement might look like, just divide by 1,000, and those are the rough order of magnitudes here. Things don't really start to change until you get down to much smaller than that. So just to show off sort of the things that the model can do a little bit, we've got power flows for all the different components that I've modeled here. Energy use is high, almost 50,000 watts per person. And most of this is because we are providing a fair amount of artificial light to the food farm, and growing food is an energy intensive process. There is natural light provided to the food farm as well, but just the data that I had has the farm growing on multiple levels, as well as on the order of like 18 or 20 hours a day. And so in order to squeeze all that growth out, you need to provide artificial light as well. But there are probably designs that you can get away without it, and that would bring down the power footprint significantly. You can see a lot of power is, of course, used for the propellant plant as well, but also other things. Water, probably the largest flow commodity in the whole system. Haven't talked much about that, but we need on the order of 500 kilograms per day per person. Much of this, of course, is recycled, but this is how much has to be supplied to these various components of the system. And again, a lot of it is going to the food growth, but also a full 40% to human consumption. Overall, the mass flows for the different components is on the order of kind of 1,000 kilograms of stuff moving around per person per day. This is not just water, this is sort of everything. This is including things like concrete, steel, glass, etc. But just as it breaks down to the different components. Flows that support human activity in one way or another is roughly 20% of this flow. And then flows for the cement plant, other kinds of industrial things are all shown here. It's just a way of kind of visualizing the total activity. Finally, the infrastructure masses, I've given you a snapshot of that from before, but here's where the concrete is used and the steel. You can see the glaring largest piece is, again, it's this food farm. And this is partly because of the assumption that I'm building all the different structures, the different levels of the food farm as well as human habitats out of steel and concrete. And maybe there's a way of doing this more efficiently, but given the data I have now, it just takes a lot of this material in order to build these rigid structures. Total infrastructure mass is about 500,000 kilograms per person for a fully built out industrial ecosystem. And finally, in the last couple of minutes, and I know I'm starting to run out of time, I want to leave time for questions. What do the interplanetary logistics look like? So I just wanted to quickly show you kind of what I have calculated thus far, acknowledging it's very much a work in progress. So at 1 million people with sort of 20,000 people a year coming, and this is very squishy, we estimate that we also need about 11,000 tons of specialized materials to be imported, which is very low. So this, together with the mass of the people and supporting infrastructure for the journey, we're looking at a payload of about 41,000 tons a year. Per synodic cycle, this is roughly 90,000 tons. And given the parameters of the BFR, we're looking at a fleet of almost 600 ships coming every synodic cycle and then returning to Earth. And then I just did some calculations of given how long the launch window would stay open and the number of ships per day that could that could land. We're looking at a launch pad facility of roughly 19 or 20 to be able to handle that. And that's assuming that a ship can land, unload its cargo, get refueled, and take off again back to Earth, all within 24 hours, which is extremely optimistic today, but maybe in a few decades of practice, we could get to that level. So with that, I'm going to stop and ask for any final questions people have.
Jeff, this is Brad. Excellent work propagating constraints and figuring out where economic opportunities are. I applaud this.
Thank you.
I wanted to make a simple suggestion based on a comment that was maybe 15, 20 years old. Alex Ignatieff might remember this. There was a guy who was talking about T.I. Lin or something like that, talking about making concrete on the lunar surface, and somebody pointed out, I think it was Ed McCullough, that if concrete existed on the lunar surface, we would mine it for its water. A solution that was developed by Baruch Kushnevitz with his contour crafting NIAC was to use sulfur. It turns out sulfur is actually pretty stable. It's a chemically resistant concrete. It has really excellent properties. It works for the moon. It works for Mars. And there's a lot of sulfur in the lunar polar regions that is considered to be a problem. It could be a resource. Yes, and there's actually a lot of sulfur on Mars in the gypsum deposits.
Yes.
So a guy at Michigan Tech, Paul Van Susante, has been working with SpaceX, Paul Wooster, on how to mine the gypsum for both water and sulfur on Mars. So if you substitute sulfur for your concrete with water, there may be better uses of water other than making concrete. Sulfur is a nice substitute.
Love it. Yeah, thank you. I was aware of the lunar concrete with sulfur. I wasn't sure how, this is why we're having this conversation, because folks who have been looking at this longer than me can kind of give the fuller arc of it. So I was aware of that, but I'm glad to hear that there's sounding more promising than I had originally surmised. So I will look into that.
I think this is a really great foundation to try to build off of, Jeff. So I really wanted to give you that feedback. And I think the thing here is one, this allows you to do a couple of things, kind of lets you bound the problem, so this is not the way, this is just a way.
Exactly.
But it gives you some kind of idea that this is not a trivial, but not an impossible, kind of thing that we're talking about. Challenging, certainly. And then it starts showing you where's the long poles in the tent, which I think is the other thing. So if you were going to say, okay, if you were going to had some money to invest in new technology or alternative technologies, where would you target that at? And where do you get the most bang for your buck? And then the other thing that I think you've acknowledged here is there's some new technologies that are coming along. And I think the exciting thing about this is you could, build in on-ramps, is we could use voltaics, but now if some of this nuclear or some of these new, let's say, one of these fusion guys works out,
right.
And you could, target that in. How would you build an on-ramp for those kinds of technologies?
That's right.
And
it would have a cascading effect, because if you don't have to build PV, then there's a lot of other resource flows that wouldn't be needed and could be, could shrink the footprint or the power requirements significantly.
Well, and the other part of this is that with some of these things, and you could start using direct energy conversion, then your heat rejection goes down a lot as well. And so that huge amount that you had in heat rejection, could be reduced as well. So there's some, but until you look at this from a system engineering and a system perspective, you don't understand the gazintas and the gazautas. You really don't know, if you pull on this one thread, how does this affect the other pieces? And so I think having this more system perspective is essential to really do any kind of meaningful trade-offs. So
Thank you.
Well done.
Thank you. Thank you.
Jeff, this is George Nordos. I'm with MIT's Strategic Engineering Research Group, led by Professor DeWeck.
Hi.
This was an amazing presentation. I have something to suggest regarding the first part of your presentation. You spoke about money and dollars and how these might be folded in. So I've been looking at that. That's part of my work. And one way to deal with it is not to use money, but to use a physical measure, such as embodied energy. Embodied energy has been developed by ecological economists to measure footprint. I'm sure you're aware, based on your background. Yes. And I've written my thesis on how lifetime embodied energy can be used to be a cost metric for all sorts of trade studies and architecture studies, especially in the context of developing an industrial ecosystem on Mars. So I'd be happy to link up with you and to just send you what I've done, and you can have a look at it.
Oh, I very much appreciate that. Thank you so much.
Thanks.
Okay.
Jeff, this is Elliot Carroll from Lunar Resources.
Mm-hmm.
You looked into using or beaming power from space to Mars?
I have looked into power beaming generally in a number of contexts. I've never done that a concept of, so you're talking about like in Mars orbit to the surface, or all the way from the Earth system? What did you have in mind?
In Mars orbit to the surface.
Okay. Yeah, interestingly enough, I was working with some folks at Caltech a couple of years ago, and we were looking at Mars ISRU concepts for making, methane oxygen. And Harry Atwater and Sergio Pellegrino's team were represented there, and they're working on space solar power concepts with power beaming to the surface of Earth, and had identified that as a very important enabling technology. Obviously, because you get away from the dust problem. Right, plus the ability to sort of send it wherever you need on the surface in principle. So I haven't looked at that as kind of like the main way that you would get your power, but would certainly be open to entertaining that.
Thank you. Very nice presentation.
Thanks, Elliot, for the comment.
Jeff?
Yes.
Doug Plata here.
Yeah.
In your farm, did you, is that multi-level, or is that just a typical footprint for farms?
No, yeah, that's a multi-level. It's a little vague how the farm would be organized, but the way it's based, I'm happy to share with you kind of the data that it came from. It's really from a Japanese study that is looking at providing full nutrition and caloric intake for a set of astronauts. So it's a mixture of vegetable and animal sources. So the animals would be sort of fish and crickets, I think. Yeah, I know, can't wait. But yeah, the idea is that it was done in a sort of a compact modular arrangement with a mixture of artificial and natural lighting. And it could be organized really in as many levels as necessary. The detailed engineering of the lighting has not been done. I think there are some very good studies out there that have started looking at it, but I have not done that for this. So we're pretty flexible. And it was really just sort of a notional idea of how much space you need between different layers, given that some plants will be short, whereas others might be several feet tall if you're growing, fruit trees or something like that.
Right. Okay.
Thanks.
Any more questions? We gotta wrap this up pretty quick, but if
yeah,
a burning question,
Or comment.
Questions, observations.
Hey Jeff, this is Lynn Harper. I used to be chief of advanced life support in the early 90s, and at that time we could grow 7,000 dwarf wheat plants in a square meter, and provide all, and using a strategy of succession planting, provide all of a single individual's food energy from plant products within 10 square meters, or 10 cubic meters. Be glad to talk to you. I mean, that was way back without genetic engineering or modification or anything else. So your numbers are good.
Thank
you've got that type of diversity, and that's about right in terms of the footprint.
You want to mention
cool.
products?
Oh, well, once you go to that type of agriculture, paper products are easy to get.
That's right. I don't think I want to start
at that point. But, you're not recycling into food, but still,
you're keeping it in the ecosystem.
Yeah, I mean, you can always reuse, you can always compost that material, so it really is quite closed. I was going to point out, and I would love to be pointed towards the best state-of-the-art, kind of study on what it takes to grow the food. The one that I found isn't necessarily the best, I think, and one thing that I think was a real smoking gun, just to share with you, is they had a very small labor input assumption, which turns out to be at this scale, half of all the people in the colony would have to be farmers. And I thought, I think you're going to need some more automation.
Yeah, you can automate a lot of this.
You can. Yeah. So we have
Jeff,
to
can you say a word about the computational environment of ASTER and whether you plan to make it open source or there's a way to link to you?
Oh, well, long term, I would like for it to be an open source platform that anybody can use. But currently, it's an in-house tool that's very much in development. It's currently, I mean, the computational platform may change over time. It's currently just a set of kind of spreadsheet inputs, that sort of form the database. And then the computations are done by sort of pulling all that data together and doing weightings to make sure that all the mass and energy flows balance. But talking with some software friends of mine, at some point we may have to rebuild it in something that's going to be more robust. And of course, I would love for it to be web-based, cloud-based, and available. But that's probably going to be a couple of years. But if you're interested in helping to develop it or otherwise contribute, let's talk, because I would love to have some more help. Oh, you're on mute. Sorry.
Jeff?
Yeah.
Doug Plata again. How much of your work is really Mars-centric versus lunar?
It's not especially Mars-centric. It's the focus that I did in the last month or so in order to make a concrete example. But many of these technologies are designed to operate in either environment. And as I said, I have a set of sort of local resource assumptions, regolith composition, sunlight, gravity, et cetera, that allows us to easily sort of toggle between them. So, and I want to have it available to do in a zero-G environment as well eventually. So.
Suggestion from Brad on the zero-G versus other partial gravity environments. There's quite a bit of experience at NASA Glenn back in the microgravity research days on the physics of process flows. There's actually quite a bit of physics that's different if you do stuff in microgravity versus 1/6 versus 1/3 G. The scaling equations are pretty important to understand, and the folks at Glenn understand them pretty well.
Thank you, Brad. I'll reach out to you and maybe get a couple of those scientists' names so we can get some detail from them. Appreciate that.
Yeah, and Jeff, David Huntsman is actually one of our colleagues at NASA Glenn, who's really in charge of the commercial space activities there.
Okay.
He's usually on the telecon. He's not on today.
But I'm sure he'd be really interested.
Yeah, and I think he could be very helpful as well as kind of tying you into the right people in Glenn. I think that would be helpful.
Fantastic. I feel like I've met him once before. I'll check my email.
If you have the the invite list for the telecon, you'll find David Huntsman. You'll find his email there.
Great. Thank you. All right. I'm glad people are interested enough to stay on after. Any other questions?
Just one parting comment. This ties in with actually something we were interested in doing years ago now. We were calling it kind of sim space. That's right. We were looking at, remember SimCities? Remember?
Yeah.
Said, okay, hey, we really need the same thing for space, and we kind of had the same idea. Jeff, something that eventually would be largely open source, that would have essentially validated physics and economic modules that people could contribute to, so you could do just what you want to do here, do some serious simulations of large, developments in space. So again, I applaud you. I think this is something that really is needed. I think if you haven't, I would think Elon might be interested in seeing some of your results.
Yeah, well,
you want 1 million people on Mars? Okay, here's what's going to take.
I'm kind of wondering what they've got in-house, but would be, of course, delighted to contribute to that in any way. So I'm kind of waiting until it's a little further along before I introduce it to him. But
yeah, no, I think at the right time, I think he would be the right person to. And we have routes there as well. So if you reach a point where you'd like to put something in front of Elon, let us know and we can help with that.
Great, Dan. Thank you. Yeah, we'll be talking again soon, I'm sure. Okay.
Anyway, I think on that note, let's go ahead and call it a day. Thank you.